Brief introduction about me. So I'm a solution consultant at Sahaj. My background is in physics. I've done research in quantum fluids, deep learning, and turbulence. And then when moving to commercial data science, I work in marketing, technology, telecommunication, and in tech scale up doing code generation and machine learning use cases and Gen AI use cases. So this is the outline of the talk. So I'll start with the basics of recommender system. So if you're not familiar at all with the recommender system, I will describe what they are, the different types that exist. Then I will discuss the cold start problem, what it is, define it, and then the different approaches that you can use to solve this problem, like hybrid models, bandits, two-tower recommenders. We will see that. And the last part will be about a practical use case that I worked on, which was recommending internet plans. And I will describe a content recommender that was tackling the cold start problem, the lesson learned, and then about the deployment strategy for production. So let's start with the fundamentals. So what is a recommender system? So basically a recommender system connects users with items. Items can be movies on Netflix, songs on Spotify, products on Amazon, and basically predicts the user interest in an item and suggests things that are likely to enjoy. So you always probably found this, you always faced with this kind of system in real life. And there are many approaches to recommend the system. One very common approach and very powerful approach is collaborative filtering. It's a series of actually approaches, but the general idea is that what you call it, the people like you method, and use the wisdom of the crowd approach and find users who have similar tastes to you and recommend items that your neighbor like, and relies on this user item interaction matrix based on what you like, what you watch, or what you bought. And it's the digital version of people who bought this also bought something else. And again, there are many approaches to collaborative filtering. One of the most important is matrix factorization. It was introduced around 2009 for the Netflix price of $1 million. Like 2006, when Netflix was still DVD by mail, they offer a $1 million prize for whoever will increase the accuracy of 10% of their system. And in 2009, someone won that prize introducing this matrix factorization approach to collaborative filtering. There are a lot of good things about collaborative filtering, but also some downsides, in particular, the cold start problem. So whenever you have new user, it's difficult to find what is similar to new user because you don't have no data about their taste and their neighbors. And then you have the new item problems. Whenever you introduce a new movie, a new song, you don't have any interaction between the users and the items. So you cannot recommend the new items. Another approach, very common, is like content-based filtering. You can call it a you might also like method. So basically focuses on the attributes of the items. So you build a profile of a user taste based on the features of the items they liked in the past. So you can have different metadata like genre of a movie, the director, the artist, the product category, depending on the kind of item you want to recommend. For example, here is if you watch Blade Runner, which is a movie by Ridley Scott and is sci-fi, you might like as well Alien, which is also similar characteristics. This is solves some of the cold start problem, but has some other issues, like the limited serendipity, which is one of the pros of the collaborative filtering. So basically, content-based filtering struggles to recommend items outside of the established interest, so it doesn't recommend things beyond what you usually like. And it's still the new user problem, because if you have no interaction history, you have no content profile to match against. But at least it solved the new content, new item history problem. There is another approach, which is the multi-class classification. So let's say, given what we know about the user right now, which single item from the catalog are most likely to click on next? And this is a classification task. So in this case, each item can be considered a unique class. And this doesn't work if you have millions of items, because you cannot have a classification with millions of classes, but it works if you have, let's say, 10, 5, or something like a few tens. And in this case, the inputs are the user features like country, device, language, and the contextual features like time of day, whenever they logged in, and so on. And as models, you can use classical classifiers like gradient boosted machine or neural networks that solve the problem. And as output, you get a probability distribution across the different items, and we recommend items based on the highest probability. So you can have a ranking of the different items you want to recommend. So we've seen a few of these possible recommended systems. And now we look at the coastal problem. So it's not a single problem, but a few problems. Like we mentioned already, the user cold start. Whenever a user sign up, what do we show them first? Or the item cold start. Whenever a new item is added to the catalog, how do we get it in front of the right people to gather the data? And then whenever everything is from scratch, you have the blank slate problem. Is the entire platform new? How can you recommend anything to the users? So there are different strategies to tackle the coastal problem. One is the simple non-personalized baseline. So you start with, if you have zero data, personalization is not possible. So you rely on metrics like popularity. So for example, you can use the most popular or trending one. So you see whoever is engaging with what and recommend that. Or you can base on top of top rated, so the most star on Amazon on the product. Or you can also recommend just the recently added items based on whatever is recently introduced, so you can recommend those to gather data. And it's like a common strategy for a brand new system, this approach. Another approach is the demographic or profile based. So basically, you assume that similar demographic profiles have similar tastes. And so we use the data we have, for example, from sign-up form based on their location and so on. You can make some first guess about their interests. And you can do some clustering approaches as well to group together similar users. Another approach is like you can just ask the user, like for example, Netflix asks you whenever you sign up for a few movies you like, or Spotify asks you for your favorite artist. And so you can build a content-based profile for the user, and then you can start recommending users to the recommending item to the user right from the beginning by asking their preferences. There is then the hybrid model architecture. Is like uses two kind of features. Uses the content features like the metadata about the item, like the genre, the category, the tags of the item, and then you can use like contextual or user features. It can be like, again, country, device type, time of day, language, and so on. And the goal is to predict the probability of interaction between a user and an item using all available features. And this use two kind of feature, and this can solve some of the issue with the coastal problem. And I'll show you one approach that was used, which is also a hybrid kind of architecture. Then there is another strategy called multi-arm bandits. So an arm bandit is what considered like a slot machine. So let's say the problem, you are in front of several slot machines, and everyone has an unknown payout rate. So your goal is to maximize the winning. So what is your strategy? So this is a classical explore versus exploit problem. So the exploit will be for you to keep playing the same machine that has performed the best so far, which is the safe bet. But at the same time, you want to explore, because if you want to try a new machine or someone that you use less, to understand if it's a better machine than the one you played before. And so you want to define, you find a new winner. So there's like a trade-off between explore and exploit. And this method has framed it in a mathematical way in order to optimize the winning. And how is this related to the recommender system? Well, in this case, each item is a slot machine, and a user interaction is the reward of the machine. And a bandit balance is showing proven popular items, the exploit, with testing out new or niche items to gather data, the explore. And this is the good advantage for the coastal problem, because you inherently get exposure to the unknown items, new items in a systematic way. And this is a very popular strategy. It's an old system, but is used nowadays. For example, this paper, a preprint from September this year about Spotify using contextual bandits to do calibrated recommendation. Basically, the problem they had is that they have so much information about music, but they want to explore also recommend audiobooks and podcasts, and so they had an issue with recommending that, and so they use a contextual bandit in order to optimize this process. And contextual bandit is just a different version of bandits that use contextual features to improve the recommendations.
So say it again about the paper of Spotify. They were trying to use
the
the learnings from one bandit just for another problem.
Yeah, so no, the problem is that if you use the other approach they had in the past, also some bandits, they were recommending always songs because their data set was biased towards songs, but now they want to push more toward audiobooks and podcasts, so they introduce these contextual bandits to diversify the recommendation. Yeah. And then another approach is the two-tower model. It was introduced in this seminal 2016 paper by YouTube about recommendation in YouTube. It's like been a very important paper of more than 4,000 citations, and it's used all across the industry since those days in 2016. And basically use two neural network approach. So there is the user tower, which is a neural network that processes the user features. Again, it can be discussed before, like demographics, context, and so on, and output an embeddings that represent the user taste. An embedding, if you're not familiar, is like a vector that represents the semantic meaning of some item. It could be a word, an image, and so on. And so it's good to getting together similar things in the same space. And then there is like the other neural network, which is the item tower that processes the item features. It can be, again, the content metadata we discussed before, and output embedding that represents the item. And then the model places user and items close together in this embedded space. And this is like can be considered also a hybrid approach because you use both the user features and the item features. And it's good for tackling the cold start problem. And again, it's used in many recommended systems, starting from YouTube and all the others one. And in this paper by YouTube, they use also a multi-stage approach, not just the two-tower recommender, but they use a later stage after the recommendation from the two-tower. They pass it through a re-ranker to even improve better the recommendation. So in general, all these big companies use a combination of all these approaches to get the best possible results, depending on the specific recommendation they need to do. So now we'll discuss the approach for a specific use case that I worked on, which is recommending phone or internet plans. So let's say you want to recommend the best phone plan or internet package to existing customer for upgrade. So let's say you have 5 and 50 items you want to recommend. So what can you do? So in this case, you don't have the user called start because all are existing customer, but you have still the item called start because you can introduce new plan package and you don't have data regarding that. So all the approach was a multi-class classification, which I mentioned before, and it was working well, but it was suffering again from the cold start problem because you don't have data whenever a new package is introduced. And originally I built a first version to approach the cold start problem using a multimodal approach. And it was successful, but still suffer from shortcomings. And yeah.
So the cold start problem in this case is just with the new planner package or users as well?
No, just plan, because this is a existing customer base. So if you want to upgrade,
upgrade then you would.
yeah. But you can generalize also to the other one. But in this case, just the item cold start. Yeah.
Okay.
And so, yeah, so I was was looking at this book, so Designing Machine Learning System. It's a pretty good book by Chip Wen, and she presented an approach for a recommended system to predict the app a user will most likely to open next. And she has this diagram, and she described, given the problem of predicting an app a user will most likely to open next, you can frame it as a regression problem. The input is the user feature, environment feature, and an app features. The output is a single value between 0 and 1, denoting how likely the user will be to open the app given the context. So she frames this problem as a regression problem. And you can see in the diagram, you have user feature, environment features, and app feature all concatenated in a single row. And then you have a label or the prediction, which is a value between 0 and 1 that you want to score how likely it is the user to click on that app. And I will show you how this will fit in our problem of recommending phone plans. So this, I will build the training set for your model, similar to what was shown in the book. So you can frame it again, like it was said, as a regression problem, but I tested also a classification approach, which showed actually to be even better. And so this is how you build the training set. So you have, for each customer, you do a cross product between the customer ID and the customer features with the product you want to recommend. So you have a number of rows equal to the number of customer times the number of product you want to recommend. So you can see here, so for each customer ID, you have the customer features and then the feature of the product you want to recommend. In this case, it's price for the plan and speed of the internet plan. And then for each customer, you have, let's say, 5 rows, 1 for each plan you want to recommend. And the way you build the training set is that you set the target equal to 1 whenever a user upgraded to that plan, and you set the target equal to 0 if the customer didn't upgrade to that plan. And so this, you build a training set just on the customer that upgraded to some plans. And so this way you build this table, and you can frame it as again, a regression or classification problem.
Sorry, one question.
Yeah.
The plans that are used for the existing plans, not the new ones I used.
Sorry, what?
To build this training set, I'm assuming the existing plans were used.
Existing plans, yeah. But and then yeah, so in this feature, the customer features, also you have the previous plan, and then you have the features of the plan you want to recommend, to which to upgrade to. So you have both features of the past plan and the future plan, and both are combined together in the same row. This is the different approach to this problem. And yeah, so when you have the training set, you can train your model like a regressor or classifier. And then whenever you want to get a recommendation, you score each customer product combination and you get a propensity. So whenever you do a classification for a regression problem, you automatically get like a real value. And instead for a classification, you can get like predict the probability of the likelihood of that particular class. And then you rank each product customer combination by their propensity. And you take the top one, which has the highest propensity, and that would be your recommendation. And then you have so on, you have the second one, the third one, and so on. So you have a ranking of all the product based on the user. And the good thing about this approach is that if a new plan is introduced, we just need to add an extra row for each customer to the scoring table, and we know the feature of the plan we want to recommend, so we just add an extra row and score again, and we have an extra possible recommendation. In this case, again, the feature are just for simplification, like speed and price for the plan you want to recommend. So again, this is working out of the box for the cold start problem, because it's very efficient to solve this in a simple way.
So the probabilities on the thing, they will all add up to like 1, right?
No, actually no. Yeah.
Because like for each and every customer, it will add up to 1, but for all the customers, it could be.
Yeah, actually, not even for a single customer. The way it's built is not adding to 1. Yeah.
Oh,
But we don't care that they are not probabilities. They are just propensities, let's say.
okay.
And so we just care about the ordering.
Ordering. Okay.
And that's why also the reason you can use also a regression approach, because you don't need like calibrated probabilities or anything. You just need a score, and the highest one is the one you want to recommend.
Okay.
And then, so to analyze and to assess the quality of these models, you can have two kinds of metrics. So the metrics of the initial model, so it could be the regressor, the classifier. So for this training set I just showed you. And so if it's a regressor, you can use the standard metrics like mean absolute error, R-square. If it's a classifier, you will use like, in this case, better to use a raw KUC because the data set is highly imbalanced, because you have more zeros than 1, because you have one per number of, let's say if you have 5 plans you want to recommend, you have 1 1 and 4 zeros, so it's highly imbalanced. So you want a metric that takes into account the imbalance of the data set. And so this is the initial metric you want to monitor. So based on the classification regression problem. But then the metric you're more interested is the recommendation metrics, so which are more important, related to your business outcome. So basically, how accurate are your recommendation? So to evaluate the accuracy of the performance of the recommender system, there are several metrics you can use. The common one, a simple one to understand also, is the accuracy at K. So it's basically the proportion of customer with correct recommendation in top K recommendation. You can also do accuracy just for speed or price, for which, or you can use other standard metrics for recommended system, like mean, average, precision, mean reciprocal rank, and so on. And the important thing is to calculate these metrics out of time. So you do a training on a certain time period, and you do the evaluation on a later time period in order to simulate what you will do in the actual real environment. So whenever you train on something, you evaluate at a later stage. And another point is that not only the top recommendation is important, because sometimes you might have some business rules that prevent the top recommendation to be actually recommended to the customer. So sometimes you want also the second and third and so on recommendation to be good, because they might be actually recommended to the user. So I'll go now into the kind of model I tested. So for the regressor approach, I use classical approaches that are usually very good for tabular data and regression data. Like you can use XGBoost. If you're not familiar, it's like a gradient boosted tree classifier regressor, like a model. And you can use also AutoML, which is like a suite of model that is automated to create the prediction with hyperparameter tuning built in and so on. And it's available, for example, Google Cloud and other system as well. And yeah, so the idea was to take first XGBoost, because usually it's probably the best tool that you can use for tabular data for regression and classification. And for the classifiers, same thing, also XGBoost, but XGBoost classifier instead of regressor. And the out of time raw KUC, so the metric for the model was actually very high. It was 0.9. So, and if you're familiar with raw KUC, so 0.9 is very good. And let's say for a random model is 0.5, and the perfect model is 0.1.
So what was NNP here, like the dimension of the data in this project, like the number of observations and the features?
Oh, was like the features were about 100 or something,
Yeah.
and then the number of customers were a couple of million.
Wow.
Yeah, maybe 10 million. Yeah. And
But what do you recommend here?
so the phone plan.
Can I ask?
Yeah, sure, yeah.
Well, I just wanted to, it's important for me to hear, and that, but more also important to hear, you know, there is a large action space when we want to recommend one item over, let's say, 1 million. So what to do that in that? This is one question. Second question, you display here a kind of scenarios that most of them could be for given scenario, meaning if I want to recommend a drug, I need to take into account the safety of the recommendation. So this is one issue I would like also to hear. And finally, I know there is a CTR, click to rate.
Sorry, what? Sorry?
CTR, it's called. CTR, it's click to rate.
Ah, click through rate. Yeah.
This is another, you know, accuracy you can model. So if I can see how you can also build on that. And finally, the long tail distribution. You are looking here per person, per item. What in terms of the whole system? The whole system, if I am YouTube, I could see most of the solution here propose a long tail distribution, meaning that after a while, we can see that most of the recommendation is working with popular item and a less unpopular item. So it poses like long tail distribution. So a new item or fresh item will be difficult to, you know, to explore.
Yeah. So
do we need another approaches to tackle like reinforcement learning? Or?
I mean, you can use also approaches to reinforcement learning and like the bandits are kind of a reinforcement learning approach. There are so regarding the long tail distribution and the recommendation regarding the new items you recommend, I will discuss that as well.
Yeah.
But basically, after you do a recommended system, you want to see how is the distribution of recommendation, and if it's aligned with what is good recommendation for you. And you can see what is your expectation of the recommendation and how often the new item are recommended. In subsequent, we also evaluated, and this approach actually worked well for that, recommending the new items also a significant number of times. So the approach that address the coastal problem, yeah. And then
in terms of large action space, meaning that you have 1 million items. So
yeah, in this case, in my in the use case I worked on, there were like about 20, like not a million. So that's why this approach is something. I mean, you can do also for this approach. You can use also for more items, but probably you wouldn't use for 1 million items. So this is not a good approach for, let's say, a recommender for Netflix or Spotify. Yeah, but what regarding the action space? So
well, I think if I have 1 million items, so I can, let's say, recommend a vector in the n dimension space.
He explained the first section. Collaborative filtering is like a large space commander. So
yeah, what you recommend there? So you know if you have 1 million items,
yeah,
so
you
the
can
output you have 1 million.
Yeah, you can rank like 1 million items, and
no, I don't think it's a good solution.
I mean, YouTube is working on that. So basically, you have like a retrieval system.
I even don't think YouTube working like that. You don't recommend 1 million.
No, you have a second
You
stage.
need to sorry. You need to have some filter to.
But I mean, what I know about like a Netflix and
Oh, it's okay.
is like you have like a retrieval system, which is a large space recommender.
Yeah.
You're not using that system to rank, but also only to filter the top of 1,000 items.
Yeah.
And then you use like a smaller one to rank them.
Yeah.
yeah, I mentioned in the two-tower model. The two-tower model is used for the first like candidate generation. It's about 1,000 or so, and then you use like a more powerful but slower model to re-rank, let's say, those 1,000 to then get like the top 10 that are best that you recommend. So use multi-stage approach.
How you tackle the safety of the recommendation here?
So the safety. So
Think of drug.
yeah. So depends on the problem at hand. So let's say if you have a collection of items, probably they are saved already to recommend. So maybe if you have some special items that are forbidden for certain users, let's say for age restriction and so on, you can use on top some business rules to filter out those recommendations. For example, I mentioned here that not only top recommendation is relevant because there's some business rule for eligibility. This was not about safety, but was about business rules regarding some customer not to be eligible to some discounts and so on. And you can do something similar for safety. So, or for age restriction, you can put some business rule on top of the recommendation to the limit to what you will need.
I think it's more difficult on 1 million items to fix the problem. So it is like a smaller problem.
You know,
Or maybe like 1 million.
even I can say to you, most of the problem that I think as a data scientist face, when I want to recommend something, let's say between even 200, yeah, not million. Now, what I get by the end of the output is, let's say, probability of each item, yeah? But most of the probability are 0 dot blah, 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 0 dot 1, 0 dot, so you don't have, you still have, you choose the best one, but the probability is too low. So when you think it, that's not sufficient for me.
I will check it.
And then my intuitions.
No,
It could be that there's the feature not very powerful in prediction power,
Yeah.
or there has to be a different choice in the type of product that you want to recommend. You can do pre-selection through a marketing strategy as well.
Yeah.
But maybe we can discuss again.
Yeah, no problem. Was another question or no? No. Okay. Okay.
At the end.
Okay, sure. Yeah, so this we already seen. We're here, so discussing the kind of model I tested first, like XGBoost and AutoML, that are usually the default one that are good for this kind of models like tabular data and so on. And then I look at also the feature importance based on SHAP. SHAP is a package based on the Shapley value, and is a good way to estimate the feature importance and attribution to certain features of the prediction. And it was a sensible kind of outcome, in the sense that the top features for these models were the price and the speed of the plans that were before and after the upgrade, and some demographic feature they will expect also to rank to the top. And the final recommendation accuracy was higher for the classifier compared to the regressor, but not very much difference, but still higher for the classifier. And the overall accuracy improvement compared to the previous solution for the coastal problem was massive, was like 40% increase in overall accuracy. So it was a success to some extent, but however, then I investigated the performance of the coastal problem. So the first thing I investigated was the propensity that were aligned with the number of recommendation. So based on what you were saying, you want to see the recommendation make sense and there is a good distribution. And first I look at that thing and seeing that the recommendation were aligned with the actual upgrades distribution to the customers. And so it was okay, it was good. And then I started to see if it will work for actually new plans that were recommended, so to address the coastal problem. And so I introduced some fake plans interpolating between two plans to see how this system will react to these new plans introduced. And I found out that basically XGBoost couldn't interpolate. So the new plans were almost never recommended by the system. And then I realized that the same they were getting same propensities for different plants by the way the gradient boosted and tree-based model work. So this was not a good approach for the coastal problem, even if the accuracy overall was good, but still was not good to address introducing new plans to the system, because these new plans were not being recommended. So not success to some extent, but not success regarding addressing the coastal problem. And so the idea was then, instead of using a gradient boosted, which is not very good at interpolating things, the idea was to replace it with something that is good at interpolating. And neural networks, even if usually they are not very good for tabular data, they have the advantage that they have good at interpolating things. They're good at approximating function, and you have a overall smooth recommendation in general. In this case, the accuracy only slightly dropped, but it was much better interpolating and extrapolating on new plans. So these new plans were recommended a significant number of times. And also the kind of journey from one plan to the upgraded one was getting reasonable results, making sense for what a customer will actually be upgrading to. And so this approach, replacing the XGBoost with the neural network, actually addressed the cost problem. And to improve the performance, I use some hyperparameter tuning, like I use a Bayesian optimization through the Vizier tool in Google Cloud, and using as the raw KUC as the tuning objective. I used the regularization, dropouts, and the number of units was, the number of layers was not so deep, so like three hidden layers. We had tuned the learning rate as an optimizer. We use the Adam optimizer, which is a standard optimizer, and it's usually performing very well. And as activation function, we use ReLU. So pretty standard neural network. You don't need a very fancy or very deep neural network for this kind of problem. But this worked quite well, even relatively simple neural network. And so in particular, I built the system using the neural network from BigQuery ML. So BigQuery is the data warehouse system by Google Cloud, and they allow you to build also machine learning model directly in SQL. So it can be very quick to test a model directly in SQL on your data directly in BigQuery. And so overall, the accuracy improved at 37% over the previous solution, so which is slightly lower than the 40% of XGBoost. However, it was much better recommending new plans compared to the XGBoost one. So for example, here I put the new plans were recommended, let's say 5% of the time, and there were about 20 plans. So it's roughly in line with what we expect for a new plan to be recommended.
If I maybe can ask,
Yeah.
you mostly, by the end of the day, you build one model. So in most of the approaches you are using, you build one model for each approach.
What do you mean? So this is a single.
Meaning sometimes I'm more adept, let's say, building 5 models with the same approach, but balancing the data before I push it to the model in different ways. Okay, so I have, let's say, from one approach, 5 models. Then to decide, I build a voting system. Could be possible for you.
Yeah, so depending how you mean by multiple models. So again, I tested
the same model. Let's say XGBoost, yeah.
Yeah.
So you build one model. You have one model, yeah. This model see the data, and now it's performing with the parameters that based on those data, yeah. So I change the data. I make some, let's say, new sampling of the data. Okay? So you train, evaluate, and test, yeah. So I change the data. When I change the data, I can propose more models, and each model maybe could be less accuracy with the other, but in the internal property of the model, also there is some changes when they deal with the new data. Okay, so I push the same record for the 5 models, let's say.
So you do a sort of a cross validation.
Yeah.
So subsampling and cross validation.
No, I don't make cross validation for each model. I build the full pipeline of the machine learning, ending with one model that should be working. But in case I want more accurate let's say, a result, if I have 5 models from the same model or even 15 models, yeah, so I make a voting system, meaning I give each model some weights in how it, let's
Like
say,
an
contribute to the final,
sampling.
yeah.
Sampling, or like you can do some stacking of different models. But if you just select the
No, not sampling, not stacking.
Ensembling. Ensemble. You have multiple models and then you collect information to get the final answer, basically. It's like
Yeah,
a voting system.
You know, because you know what, in general, what I am afraid is building one model in same, let's say, that pick the same data, okay? And then going with this model 2 months ago. So you use it 2 months, but the model see the data in some,
so that's why you need to retrain the model frequently in order to be
yeah,
data. That's why
train
you
the
do.
same model frequently in different data from the data, from the same data set that I use, yeah?
But if the
But I
if the
sampling, but I sampling.
if the data set is large enough, you don't, if you resample, you don't change the model. It will be performing the same. If you have a small data set, maybe if you do resampling, the model will perform differently. But if you have a big enough large sample, if you do resampling, it will not change the performance of the model. So I don't think it's a effective strategy for this kind of problem.
You make a resampling. So if the data is unbalanced, okay, so there is a lot of, there is about 10 different approaches that you can resample from unbalanced data. So
you can do stratify sampling, or if you want to keep the relationship. Yeah.
But I talk about the approach that having, let's say, 5 or 10 models from the same approach and building, let's say, a voting system.
Tweaking differently, slightly the training of the model, and then you have.
Yeah, but just changing the data, yeah.
Yeah.
You have a sample of models, and then you have an ensemble, and then you do a voting. That's what I think was it.
Yes, okay, I understand. Yeah, it's a possibility, but again, for a big, large enough data set, shouldn't matter if you do a sample, the model should behave similar. If it's a small data set, you might consider doing that, but if you have millions of users, if you do different samples, the statistic will be similar. And so if you don't change the hyperparameter of the model.
I'm thinking in some scenarios where I have not enough data from one side, or the data that I have, it's unbalanced data.
Yeah, no, it's interesting. Yeah, but yeah, and depending, so if it's unbalanced, like in this case, you have to use different techniques, especially for sampling. It's important, like you mentioned, like you use the stratified sampling in order to keep the ratio of negative to positive samples about constant among the different subsample. So you need to take into account that, yeah.
Also in terms of model drift, so you know, when you finish especially in the deep neural network, when you finish training and you go ahead 2 months, so you have new data, so you didn't push them to the model here, so you have new data that the model hasn't seen. So it's comes sometimes, you know, based on the scenario, we have a model drift.
Yeah, that's
so I built another, let's say, model in the new data and make the voting system. That's what I mean.
Yeah, another approach to compensate for data drift or concept drift is like retraining regularly. So have a pipeline that do regular retraining, and use like also a champion challenger approach, depending. So there are different ways to. But it's data drift is it's important to consider for sure. Yeah. So now go briefly into the deployment of this system. So we shown that it was working fine, it was addressing the cluster problem. So now it was built on BigQuery ML as like a proof of concept. Now we want to deploy it. So what can we do? So like our approach is using Vertex AI. And at the time we use like a custom Vertex AI approach, MLOps approach, and based on Kubeflow pipelines. But you have a Kubeflow pipeline for training, a Kubeflow pipeline for prediction, and different BigQuery ML, BigQuery components to prepare the data, and BigQuery ML components for the different models. and then you have a batch prediction to generate the scores, and then you use like a different tools like integrated, like you have Vertex AI to manage the whole thing, then BigQuery to connect to data, cloud storage to get the data from, cloud build for the CI/CD pipeline, cloud scheduler to trigger the different pipelines, and then you have your code stored on GitHub and all integrated in a MLOps system. And so for those who are not familiar, so what is a Kubeflow pipeline? So basically a machine learning assembly line, and it's an open source machine learning platform built on Kubernetes. So it's very scalable and lets you orchestrate complex machine learning workflows. And it basically is a factory assembly line for your recommender system. So you can see you assemble each step as a component, which is like a Docker container. Could be for data ingestion, feature engineering, training, evaluation, deployment. And you assemble these components in a pipeline. You can see a diagram on your right. Each blob is a component, and the full system is a pipeline. And the pipeline is the blueprint that defines the sequence of the steps and how the output of one connects to the input of the next. And yeah, it's like a structured way to define your machine learning pipelines. And the good advantage of this is that it's highly automated. You can schedule your pipeline to automatically retrain the model every day. For example, like you mentioned, like if you have data drift, you want to retrain frequently. So to be sure that the data is up to date and your model is up to date with that. And then reproducibility is also a good point with Kubeflow. Every run is versioned. You can perfectly recreate any model because you have exact code, data, and parameters that you use. So it's very, very good for that. And also it's scalable. It leverages the power of Kubernetes to scale up and down computational resources. And so even each component can use different resources. So if it's a easy, like a not very necessary power component, you can use a small machine. And if you need more power, you can use bigger machines. And Vertex AI has the advantage of managing all the infrastructure for you. So that's the good thing about that. And we use this called Turbo Templates, which is a production level MLOps system based on Google Cloud. It uses like standardized environments, like for testing, dev, and prod. And you can use infrastructure as code with Terraform. So it's you can manage all your crowd resources in a repeatable way. It has automated CI/CD through Cloud Build for testing, deploying all the machine learning infrastructure. And then you can have reusable components. You can build your components for Kubeflow and have a library of that you can use for a different use case even in the future. So you can build a library of components, and then it's a end-to-end machine learning pipeline. You can start with the training and batch prediction, for example, and or you have an endpoint for generating the recommendation if you want a live recommendation instead of a batch prediction. So the high-level architecture, there are 4 Google Cloud projects, like the admin one that orchestrates all the deployment across all the environments, a dev one, which is a sandbox where you can develop and build your system, a test or a staging environment, which is similar to production, but you use for end-to-end testing before the release, and then eventually a production environment where you actually you have the recommendation that reach the customers. And then the pipeline is triggered by Cloud Scheduler, and then triggers a Cloud function via a pub/sub message, which is like the messaging system in Google Cloud, which in turn starts the Vertex pipeline to run and do the training or prediction. This is the basic CI/CD workflow. So whenever you have a pull request, you have run linters, you do pre-commit hooks, you execute the unit test, you compile the pipelines, and you run end-to-end. Whenever you release a new tag, you build and push the training and prediction container to the artifact registry, and you upload the version ML pipelines to the artifact registry for all the environment. And whenever you do a merge to main for the you automatically applies the Terraform changes, and you update the infrastructure in all the environments. So this is the diagram of these turbo pipelines. It's basically what I described so far. So at the top, you see the dev environment, which is mainly for data scientists to work with the Vertex workbench, which is basically Jupyter notebooks from which you can do your experiments and even deploy pipelines, Kubeflow pipelines straight from the notebook. And it's used for experimentation and generating the initial models. And then you have the test environment or the staging environment where you have this pipeline triggered by the scheduler, the messaging through PubSub, and the cloud function that triggers the pipeline. And the mirror one is for the production environment, which is somewhat basically a mirror one of the test environment. And so for each pipelines, you have the training pipeline, which run the BigQuery job, prepare the data, extract the data, you do model training. You can have a champion challenger evaluation, compares the model that you just built to the current champion, and just if it's better than the current champion is replacing it. So you can do conditional deployment depending if the model, the new model you're retraining is better than the old one. And then you have the prediction pipeline, which in this case, again, it's a batch prediction job. You don't need to do, if you don't need like live endpoints to do the recommendation. And you can use like the Moodle lookup for looking for the current champion, and you generate the batch prediction. And then you do, for example, drift monitoring, like you mentioned, it's very important if there is a data drift or training service queue. So you want to monitor that. And this you can do with Vertex AI in an efficient way to monitor that. So here there are some links for the Vertex pipelines that I described now, and also some introduction material about Kubeflow pipeline if you're interested. And now, before ending, I just want to show you some code to make it a bit more concrete. So it's not the actual code for the recommender system. It's like a proof of concept that I built just for this to showcase. It's a simplified version just to have an idea of what the components are and how it looks like. And it's a lot of code. I will go very quickly. You don't need to understand everything. I will just point out what might be interested. So basically here I start with a notebook where I outline the whole recommender system, and then I'll show you the full repo of the pipelines to see just how it's structured, just a flavor of it. Again, not go into the details. But let's say to mock this recommender system, first I mock the data. So I create a data set based on some rules, and this is basically how it looks like. So you have a customer ID, gender, age, location, some features are added like tenure with the company. If there's a discount percentage, and the plan they're currently on, and the plan they upgrade to. And then different, let's say, the data of the plan and the cost of the plan, like I showed in the slides before. And these, for example, are the plans. For example, this would be number of gigabytes you are in your mobile plan. Could be like 20, 50, up to unlimited 1,000, and different costs for each of that. And then you generate the training set, like I showed you before. So this is how the training set looks like, exactly like I showed in the slides. So you have for each customer ID, you have a number of rows equal to the number of plans you want to recommend. You have the features, and then at the end you have the label, which is generated as a 1 whenever there is an upgrade to that particular plan, and which is a 0 with otherwise. So again, nothing new, just what I described before. And then you can train XGBoost model. I created just the 2 functions, one for generating the training test set, just using some Python to separate the train test split, and then a function to train and evaluate the models. And you can use, again, XGBoost classifier, just a binary classifier, and you fit the model, and then you evaluate it with some metrics that we discussed before, like the rock AUC for that model and the ranking based metrics for the recommender system, like the mean reciprocal rank, the accuracy. And so this is like a standard kind of way of building the train test, build the model, and get the metrics. And this, for example, is the evaluation metrics for this mock data. You can see the rock AUC is 0.6, so not very good, but better than random, which is 0.5. But again, the data was generated mostly random, so it's expected just for showing how this will look, and the different other metrics here. And then I want to just show you so how it looks the same thing done in a Kubeflow pipeline. So basically, I mentioned that you have the Kubeflow pipeline built on different components. And basically what I transfer is from the function that I define here, so the two functions, I created now as a component. So you have a decorator here, you define a component, which is again a Docker container. You define the base image, there's, for example, here Python 3.12, and you install a certain packages within this Docker container. You can use the minimum amount of packages necessary for this particular container, for this specific component. So for example, for this generate training and test set, you don't need any XGBoost model because it's just for generating a training and test. So you put just the components, the packages you need. And so you define one component, very similar to what I showed before. And then you have another component, which is for the training and evaluate model. Again, in this case, you have the base image, and then you add, in this case, XGBoost as an extra package that you want to include, because in this case, you use XGBoost as your model. And then this is very similar to the function I showed you before, but is a component. And then at the end, after you define the different components, which are mapped to the function that I showed you before, you define the pipeline, which assemble all the components together. You call it a certain name, for example, telco plan recommendation pipeline, give a description, and then you lay out the different components, how they're arranged together. So for example, the first step one is generated training and test set. So you have the first component defined here. Step two, then you have the train and evaluate the model, the second component. And after you've defined this pipeline, you can compile the pipeline and generate the blueprint of the pipeline, which is a JSON file that is then uploaded to Vertex AI for building of the model and do all you can do the scheduling, everything, and so on. And so this was like one pipeline you can build. I just want to show you, you can do the same for, instead of XGBoost, you can do the same thing with BigQuery. BigQuery for processing the data, and BigQuery ML for the modeling. So very similar. In this case, you define the first component. The package you want to install is BigQuery package from Google Cloud. You first prepare the data in BigQuery. In this case, you don't have Python code, but you have some SQL code. Here is the way to create the training set. And then you have the training model with BigQuery ML, another component, again, BigQuery as a package. And in this case, you have the deep neural network classifier by BigQuery ML, just as a SQL code inside this pipeline. And then in this case, I separated the evaluation as a separate component. Again, you can decide what works best for your use case. Again, in this case, you define the ranking metrics as, again, SQL, also again, BigQuery. And then again, you can assemble the pipeline with different components together as a single one, and then you compile it. And this is what Kubeflow pipeline looks like in code. And just briefly, last thing is I want to show you how this fits into the turbo templates or different MLOps pipeline you can do, like a note from notebooks. So this is what the turbo template repo looks like. So you have some for configuration of the cloud build for the CI/CD pipeline, where you have a YAML file for setting up the Terraform infrastructure, where you have the Terraform files here for different environments. And then you have different components to use in the pipelines, defined as Python files. And then the important parts are the pipeline files. Again, this is the training pipeline. And this is very similar to the one I showed you in the notebook. You have the different components, prepare the data, train a model BigQuery ML. The only difference is you can also put the code in a separate, for the SQL, you can separate it from the pipeline to make it more modular and separate it. For example, in these queries here, you have the prediction pre-processing as a separate SQL file that then you call in the pipeline at the end. So you define the pipeline very similarly as I showed in the notebook. So you define the different, you assemble the different components. In this case, you generate the query based on this file that again was put as a separate SQL file. And after that, you upload the model and you upload the pipeline, and then eventually you can, is uploaded to Vertex AI and can be deployed in production. Yeah, and with this, I've finished, and then I'm happy to answer any question. And if you want to leave any feedback, you can scan the QR code here.